Hi, my name's Max Ehrlich, and this is Analyzing and Mitigating JPEG Compression Defects in Deep Learning. Okay, so a lot going on this slide. We're going to be here for a couple of minutes. So the idea of this paper is that we're noticing this trend where deep learning models are being deployed in consumer settings, and this is happening at a considerably faster rate than it previously was recently. And we in academia, when we train these models, we tend to use the same kind of standard data sets over and over again. So one of the larger questions that we're trying to bring up with this paper is, are these data sets really representative of the kinds of data that users produce? So if you were going to deploy one of these models in a consumer application, do you have any confidence that it would, correctly handle real data? So we can observe that there's some disconnect here. And specifically, we picked one task just to constrain the scope of the paper and make it a more practical thing to study, studying JPEG compression. This is the most common thing that users do to their imagery. So users by and large are not applying blur and noise and things, but they are applying JPEG compression. And anyone who's been around the internet for a little while will have seen JPEGs of varying degree of compression. So this potentially is a real problem, and we wanted to study it. And Facebook in particular, which they partially funded this work, they deal with a lot of different JPEG compression, some from the users and some that they introduce. So this kind of has an important application there as well. So the two questions we really wanted to answer are, do deep learning models lose performance when you JPEG compress their inputs? And that's kind of an intuitive thing, right? You expect that they would, but also, and probably the more important question is, can you do anything to mitigate this? So we conducted this pretty large study. This was a pretty massive undertaking. We took 23 models, 4 different tasks, and 3 potential mitigation techniques. These are techniques that people might be likely to employ in a real setting. And we considered them all over 9 different JPEG quality settings. So anyone who's saved a JPEG before, a little slider will pop up 0 to 100. So we just do 10 to 90 in steps of 10. And we concluded from this that generally tasks face a pretty steep penalty on whatever their metric is for heavy to moderate compression. But the interesting thing is that the best way to mitigate it depends on the task and the model. And over here on the right, I have the teaser figure. So the triangles are classification models, the diamonds are semantic segmentation models, and the squares are detection models with also mask RCNN in there as well for instance segmentation, being quite similar to those. Okay, so the study methodology, the idea was to simulate a system receiving JPEG compressed inputs at an unknown quality so that the system can get any level of JPEG compression. So we restricted it to 10 to 90, again, just to constrain the scope a little bit. And then any mitigation techniques that required fine tuning, we're randomly selecting the quality from 10 to 90 as a form of data augmentation. We're going to talk a little bit about how we use artifact correction later, but when we do use artifact correction, this is suppression of JPEG artifacts, we use this QGAC model from ECCV 2020. And this is pretty important because QGAC does 2 things compared to other models. And one is that it has native and good supportive color images. Surprisingly, a lot of these models are grayscale only. The other and the most important thing is that it supports multiple quality settings with a single network. So if we were using the prior works, we'd have to train a new model for every one of these 10 to 90, in steps of 10. So for every model, for every mitigation, for every JPEG quality setting, we'd have a new artifact correction model. QGAC lets us avoid that. It was really impractical to conduct this study until models like QGAC started to be developed. And then our baseline is to just simply pass JPEG images into a pre-trained network. And this is what we're comparing to. So now when we look at mitigations, we have supervised fine-tuning, sort of the obvious choice where you just take your data set and you JPEG compress the inputs and you just fine-tune with the labels themselves. Off-the-shelf artifact corrections is something I've heard discussed where you just do JPEG artifact correction on the JPEG inputs, then pass them into the network. No fine-tuning involved, no training and nothing. And then what we proposed here to do was also task-targeted artifact correction, where you fine-tune the artifact correction network for the task. We'll talk a little bit about that now. So the idea here is to use loss from the downstream task to fine-tune the artifact correction network. So what you're doing now is you're saying instead of trying to make a nice image for someone to look at, instead focus on reducing artifacts that are degrading this prediction. And there's a bunch of nice properties that this has compared with something like the supervised method. It's self-supervised, so there's no labels required to train. You can put whatever images you want in here. You're just trying to match the logics. In practice, we use the same data sets just to keep things fair. So because, if you were to fine-tune the task network, you can only use it for that task. Because this is an artifact correction network, we can transfer these weights to other tasks, and it works pretty well. So even other tasks, even other networks in completely different tasks. So for example, if I was to train on MobileNet for ImageNet classification, I could apply that artifact correction network to detection, for example, and it would work. And then similarly, it supports this multi-head setup where you have multiple tasks. So it's really a good way of reusing a model, which is important in consumer applications because labeled data is expensive to obtain. Okay, so here's the basic outcome of the study. So top row here is no mitigation. So you can see like from qualities 10 to 50, these are the condensed plots. There's bigger ones in the appendix of the paper. Yeah, there's a pretty reasonable performance drop as expected on whatever accuracy we're using. So MAP and IOU for these. And then down here, this is when we start applying mitigation. These charts are kind of fun to read, but basically what you're looking at is the circles are no mitigation. So that's the same as the top row. The crosses are off-the-shelf artifact correction. The diamonds are task-targeted artifact correction, and the squares are supervised fine-tuning. So interesting thing to note here is that the diamonds and squares are more or less on par with each other, but the squares are generally a little bit better for classification. For detection, that story changes a little bit because now the diamonds are doing a little bit better at the low qualities, and then for semantic segmentation, it's just better to use task-targeted AC. It's almost exclusively better than supervised fine-tuning. So I spoke a little bit about transfer and multi-head before. So the way to read this is for the transfer charts here, the red line is what I trained on, and the title of the chart is what the model that we're testing. So this was, red line was trained on ResNet 18 and then transferred to ResNet 101. And you can see that it's pretty comparable across the board. Same with multi-head, where three model is including these three models. Two model is just ResNet 15 faster, RCNN, and you can see that it's pretty comparable. So there's a good reuse there. And then I'll leave you guys with some qualitative results just as a kind of neat thing to look at. So the top row is faster RCNN, the middle row is mask RCNN, and the bottom row is HRNet V1 and then C1 decoder semantic segmentation. So you can kind of see how the different techniques change the prediction. And then I'll be available to take questions now.